What if humanity had to live on the Comet 3I Atlas? It came from the darkness where not a single ray of the sun exists. The Comet 3I Atlas, an interstellar traveler, crosses our solar system only once in eternity. It belongs neither to the sun nor to any planet. It is a fragment from the depths of the cosmos, carrying within it the memory of other stars. But what if one day humanity decided to live not on a planet, not on the moon, and not even on Mars, but on a comet that flies through the solar system and then departs again into interstellar space? What if this celestial body became a natural spacecraft capable of carrying humankind beyond the reach of the sun? Why this could happen? There could be many reasons for such a decision. Perhaps humanity had reached the limits of its development within the solar system, and decided to take the first step toward the stars. Not aboard an artificial ship, but by using a natural celestial body. Or perhaps Earth could no longer sustain life, and the only path to survival lay in a passing interstellar visitor, the Comet 3I Atlas, which happened to pass near the orbit of Mars. It had everything necessary to begin a new life. Water in the form of ice, methane, carbon dioxide, and organic compounds. Its trajectory led beyond the solar system, into the unknown, where no human had ever gone. So humanity might have tried to use it as a vessel of escape. A frozen ship crafted by nature itself. Before we continue our journey through the unknown, take a moment to like this video and subscribe to join our growing crew of space survivors. Comment below, where should humanity try to survive next? A frozen moon? Or something even stranger? The environment of the comet. Comet 3I Atlas is of interstellar origin. Its nucleus is approximately 5 kilometers wide, composed of water ice, carbon dioxide ice, and methane ice, mixed with dust and dark organic compounds that give its surface a black, almost coal-like color. The surface temperature ranges from -200 to -250 degrees Celsius. There is no atmosphere, and gravity is so weak that even a small careless movement could send a person drifting into open space. As the comet approaches the sun, it comes alive. Jets of gas burst from deep cracks, forming a glowing greenish coma, the characteristic luminescence of carbon molecules in a vacuum. During this active phase, the nucleus becomes covered in geysers of water vapor and carbon dioxide, making it both dangerous to land on and rich in valuable resources. It was precisely during the moment when the comet passed near the orbit of Mars that it was calm enough for humans to attempt a landing on its surface. How humanity could reach the comet? Landing on a body with such low gravity would be an extremely complex task. It would require technologies capable of anchoring modules not through the force of weight, but through mechanical grip. The most effective solution would be automated landing stations equipped with harpoons, similar to the European Space Agency's Rosetta mission lander, Philae, but hundreds of times more powerful and designed to secure large structures. The first to descend would be robotic modules, drilling into the surface, placing anchors, and building stable platforms. Human habitation domes could then be installed tens of meters below the surface, where temperatures are more stable and the thick ice layer serves as a natural shield against radiation. For movement, micro-impulse jetpacks would be used, allowing astronauts to perform short, controlled hops above the surface, since walking on the comet would be nearly impossible. Every step could send a person drifting into weightlessness. Resources for survival. The Comet 3I Atlas contains everything necessary to sustain life, hidden in frozen form. Water, or hydrogen-2 oxygen, the main source of life, which can be split by electrolysis into oxygen and hydrogen. Carbon dioxide, or carbon-2 oxygen-2, a raw material for producing oxygen and methane. Methane, or carbon-1 hydrogen-4, fuel for reactors and transport systems. Organic compounds, known as tholins, a foundation for creating plastics and fertilizers. Dust particles containing silicon and metals, materials for three-dimensional printing of components. The entire cycle could be fully closed. Water is split, oxygen is supplied to the domes, hydrogen is converted into methane. Methane generates heat and electricity, and the byproducts return to the system. What appears to be a dead, frozen fragment of space could become a source of air, energy, and construction materials. Sources of energy. Far from the sun, ordinary solar panels become almost useless. Sunlight here is hundreds of times weaker than on Earth. Therefore, the primary power supply would come from radioisotope thermoelectric generators, or RTGs, and small nuclear reactors, the same technologies already used in interplanetary missions by the National Aeronautics and Space Administration. A single RTG module can provide stable heat and electricity for decades, making it ideal for an environment where there is no true day or night. This heat could be used to melt ice, warm water, and maintain the microclimate inside the domes. Additionally, methane-based reactors could burn carbon-1 hydrogen-4 in oxygen-rich chambers, and thermoelectric generators could convert the temperature difference between the warm interior and the frigid exterior, at about -250 degrees Celsius, into power. Thus, even a distant object beyond the sun's warmth could remain self-sufficient in energy without external aid. Living modules. The colony's living structures might resemble a network of sealed caverns carved within the heart of the comet. Their walls would be coated with layers of ice and dust, serving as natural protection from radiation and micrometeorids. Each dome would contain its own systems for air regeneration, heating, and illumination. Artificial gravity could be created by rotating certain modules around an axis, while oxygen would be continuously generated through electrolysis. Inside the domes, hydroponic farms would operate. Plants would not only produce food but also purify the air, maintaining a closed biological cycle. Lighting would be artificial and warm, to sustain psychological comfort and the rhythm of life in a realm of eternal darkness. The beginning of interstellar flight. When the Comet 3I Atlas passed the orbit of Jupiter, it reached a speed of about 42 kilometers per second, fast enough to leave the solar system. After that moment, the sun ceased to be a source of energy, and space became cold and empty. Sunlight weakened hundreds of times, the surface temperature dropped to about -260 degrees Celsius, and the radiation background increased sharply. Beyond the heliosphere, there is no longer any protection from cosmic rays. To survive, humanity would need to create systems that function completely independently of external sources, energy autonomous, airtight, and stable for decades to come. Orientation and navigation. Once beyond the boundaries of the solar system, the Comet 3I Atlas would move in a region where familiar reference points no longer exist: no sun, no planets, no magnetic fields. Navigation would require stellar positioning systems that determine location using pulsars and distant radio sources. Such technologies are already being developed. For example, pulsar-based navigation systems, known as XNAV, which can determine coordinates with an accuracy of a few kilometers, sufficient for interstellar travel. For communication with Earth, enormous phased-array radio systems would be needed. However, once the distance exceeds 100 astronomical units, the signal delay would reach hours, and eventually even days. Therefore, the entire colony would have to operate in full autonomy, without waiting for commands from Earth. Time and distance. Even at a velocity of 42 kilometers per second, the comet would move incredibly slowly on the scale of interstellar space. To reach the nearest star would take approximately 30,000 years, even if the comet's trajectory were pointed in that direction. This means that any colony aboard 3I Atlas would have to be a multi-generational civilization, where life continues not for one human lifetime but for tens of thousands of years. Thus, the main challenge would not be speed but the preservation of ecological stability and memory. Over such immense time spans, even the most durable materials would degrade, so technology would need to rely on self-repairing systems, robotic modules that continuously maintain the infrastructure, replace components, and rewrite data as it decays. Biological rhythms and physiology. In an environment of perpetual darkness and microgravity, the human body would gradually lose its natural orientation. The absence of day and night disrupts hormonal balance, sleep cycles, appetite, and psychological well-being. Therefore, inside the colony, it would be necessary to create an artificial circadian rhythm, light cycles imitating 24 hours, with adjustable brightness levels to support biological regulation. Gravity would also play a crucial role. It could be partially compensated for by rotating modules that generate centrifugal force, not a complete substitute for Earth's gravity, but sufficient to reduce muscle loss and bone deterioration. For long-term existence in space, biomedical life support systems would be essential: continuous monitoring of blood composition, automated tissue regeneration, and preservation of genetic material for future generations. Psychological isolation. Survival in complete isolation is not only a technical challenge, but also a psychological one. Beyond the sun, there is no natural sense of space, time, or horizon. People would have to live in a closed environment, where every event repeats itself and change occurs only through the inner evolution of the system. To prevent the degradation of thought and social bonds, a synthetic cultural and educational system would need to be established. One that continuously maintains the intellectual level of the community. These could include simulation environments, virtual worlds that reproduce the sounds of wind, the movement of the sea, or the sight of a starry sky. Such technologies would not be mere entertainment, but rather a psychological stability mechanism allowing the brain to retain a sense of reality. Social structure and organization of life. The conditions of constant isolation and limited resources would force humanity to create a new social model, where the highest value is not individual comfort, but the stability of the system. Any mistake or conflict could threaten the life of the entire colony. So the social framework would have to be built on principles of cooperation, rotation, and shared responsibility. The optimal form of governance could be a technocratic consensus system, where decisions are made automatically, based on data processed by controlling artificial intelligence modules, and humans act as operators and supervisors. This approach removes human error from critical operations such as resource distribution, energy regulation, and life support maintenance. Every member of the colony would have a defined role within the closed ecosystem: technician, biologist, medic, or communications operator. Instead of money, a resource quota system would exist, regulating access to water, energy, and food according to contribution and necessity. Such a structure minimizes conflict and maintains equilibrium within an enclosed habitat, where survival depends on the precision of every action. Technological evolution of the colony. Throughout the long interstellar journey, technology would not remain static. Comet 3i Atlas would transform into a self-renewing platform, where most functions are carried out by automated systems. Robotic modules would continuously monitor the condition of the domes, repair microfractures in the ice, replace worn components, and regenerate materials by nanorecycling dust and organic waste. Data stored in memory systems would be duplicated regularly across multiple archives, to prevent information loss over thousands of years. Artificial intelligence would not govern humans, but would act as an automatic guardian of stability, monitoring the atmosphere, temperature, the carbon dioxide, oxygen cycle, regulating radiation levels, reactor output, and biosphere balance. Over time, as reactors aged, a portion of the colony's power could be drawn from the comet's internal thermodynamic flow, converting the temperature difference between the icy crust and the core into electricity through semiconductor cascades. Thus, the colony would become more than a base. It would evolve into an integrated ecosystem, where technology, biology, and human intellect form a single continuous loop of survival. Potential risks in interstellar space. A journey beyond the solar system carries a range of unique dangers that do not exist under planetary conditions. Cosmic radiation and micrometeoroids. Even with a protective layer tens of meters thick, there would still be periodic radiation spikes capable of disrupting electronics and damaging deoxyribonucleic acid. To reduce these risks, continuous monitoring and regeneration of the comet's ice shield would be necessary. Thermal stress within the core. Due to internal heat sources, the comet's structure could slowly deform, creating fractures or gas eruptions. Such phenomena would require pressure compensation systems and early warning sensors to maintain stability. Material degradation. Even in extremely low temperatures, over the course of thousands of years, polymers, metals, and electronic components would gradually lose their properties. The only viable solution would be continuous in situ regeneration through three-dimensional printing using recycled raw materials. Genetic aging of the population. Without external genetic exchange, random mutations would accumulate over generations. To counter this, the colony would need genetic data banks and programs of periodic genome correction to preserve the health of future generations. Thus, an interstellar colony would require not only engineering solutions, but also bioethical and genetic strategies to sustain the stability of the human species on a timescale of millennia. The purpose of the journey and possible directions. The Comet 3I Atlas follows a hyperbolic orbit, moving in the direction of the constellations Hercules and Ophiuchus, a region containing several red dwarf stars, including Ross 695, Gliese 687, and LHS 458. The probability that it would pass close enough to one of these stars is small, yet theoretically possible. Over tens of thousands of years, it might enter the gravitational influence of another stellar system. If the colony were still intact by then, it could use this gravitational encounter to accelerate or adjust its course, possibly even entering orbit around a new star. In this way, the comet could become a natural interstellar carrier of life, transporting humanity to another sun without artificial engines. Such a mission would not be a journey, in the traditional sense, but a relay of survival, where life itself passes from one stellar system to another, carrying with it knowledge, biospheres, and consciousness. Biological adaptation. Prolonged existence in an environment of microgravity, darkness, and limited resources would inevitably lead to gradual biological adaptation. Even with advanced medical technology and genetic regulation, the human body would evolve under these new conditions. Reduced gravity would diminish muscle mass, lighten bones, and alter cardiovascular function to work efficiently with less strain. Generations born within the colony would possess a different physiology, shorter stature, lighter skeletal structure, and modified ratios of muscle to fat. Continuous darkness and artificial light would also reshape human vision, increasing sensitivity to the infrared spectrum, reducing color perception, and causing permanently dilated pupils. These changes would not represent degeneration, but rather the emergence of a new form of humanity, one adapted to survive in an environment where the sun is no longer the source of life, and where stability of internal systems becomes the key to endurance. Informational inheritance. For a colony lasting millennia, the preservation of biological life alone would not be enough. Knowledge, culture, technology, language, and history must also endure. To achieve this, the colony would require a system of informational inheritance, one that preserves data about Earth, humanity, and the colony's experience in multiple interconnected forms: digital, biological, and cognitive. Digital memory. Continuous duplication of data across numerous independent archives, with self-repair algorithms restoring any corrupted information. Biological memory. Preservation of cultural data within genetic structures, for example, encoding symbolic sequences of deoxyribonucleic acid in synthetic microorganisms. Cognitive inheritance. Transfer of knowledge through immersive educational simulations that do not merely instruct but recreate the lived experiences of previous generations. This would allow the colony to not only preserve its culture but also to evolve intellectually, forming a continuous chain of consciousness extending across space and time. Arrival at a new star system. If Comet 3I Atlas maintained its structural integrity over tens of thousands of years and its trajectory indeed crossed into another stellar system, the colony might eventually arrive in a region similar to that of Ross 695. Such systems, dominated by red dwarfs, have low stellar temperatures but are often surrounded by planets with dense atmospheres composed of carbon dioxide and methane. In theory, humanity could use the resources of this new system to build orbital habitats, or even relocate to a habitable planet. This would not require traditional propulsion systems. It would be enough to separate the colony's modules from the comet's core, using methane-based reaction engines or gravitational maneuvers for controlled descent. If the new star possessed a stable temperature zone and orbiting planets suitable for life, the colony could re-establish a full biological cycle, cultivating flora, creating breathable atmospheres within biomes, and gradually expanding the biosphere. Thus, the comet that once served as a temporary refuge would become a vessel of interstellar migration, carrying humanity naturally from one sun to the next, a bridge between worlds born from cosmic chance and human determination. What if comets like these have already carried life between the stars? Not necessarily human, but any form of life? What if the principle of survival does not require ships or engines, but only the ability to adapt to the motion of the universe itself? The Comet 3I Atlas shows that even a fragment of ice can become a world. If humanity ever truly colonizes such objects, it will mean we have learned to live not on planets but within movement, in a constant passage between the stars. Then the boundary between cosmic exploration and evolution will vanish. And perhaps, millions of years from now, someone in another system will discover a fragment of a comet, bearing strange patterns beneath its ice. The traces of those who once tried to stay alive in the darkness.